Hi everyone. So today we will be starting with the high level design course. Um so mostly this course will cover everything from the basics, and we will start with the kind of summarizing what I have learned from the designing data intensive applications book. Um, so I will tell all my learnings from that, and which will help build the concepts of high level design. And then what we will do in this course is we will cover some examples, real life examples of high level design, so that we know how to apply these theoretical concepts and put them into real world designs. So that is what I will be covering in this course. And so yeah, let's without further ado, let's get started. So what I'm gonna cover now is the chapter one, which is what is first data systems, and what are some properties of data systems that we are building, right? Uh, so what are the properties that are actually needed in the real world and that are emphasized when you are building any system, right? So that what I will be I will be covering in this chapter, and it will be a very introductory chapter for that sake. So going over table of contents, I will just give an introduction and talk about data systems. What are data systems? Then I will talk about three system properties that are very much needed for any software that we are making, which is reliability, scalability, and maintainability. Okay, so I will be covering these sub points in these topics. So these are the major points that we will be covering, and I will be speaking about them one by one. Okay, so so first is today's most system are data intensive than compute intensive, right? Whenever we see something like a social media app, or something like maybe just a web server where you just order e-commerce, those in each of these the actions are not so much data intensive, but the scale at which these actions are performed and the data which is managed by each e-commerce, say Amazon or Flipkart, is so much that uh, most systems usually work on much data but not very compute intensive in that sense. So these systems do almost normal things like any system on a large amount of data. Thus, they are made of following components to process data. So I will be telling the usual components. First is the database system to store data for retention. So second is data cache, which will help us store compute intensive results. Third is query cache to store search indexes, like what is the product you want to search, and there would be some index based on today's date, recent products. So those in kind of index. uh, Fourth would be something like sending a message to another system to process. So this is very common. One one service sends to another one service of a system sends a message to another subpart of the system to process something. And third is something like batch processing for something like batch queries or aggregation. So these are the simple components that usually make our data system. Let's move forward. So let us think about what is data system. Um, like we can categorize cache, database, and queue almost into we categorize it into different components, but they superficially are kind of same thing, right? They are storing data, just have different characteristics on how much time they store data, kind of thing, and whether the storage is persistent or not. But kind of like they what they essentially do is they store data for some time. um, but what is happening is, so there was a certain characteristics of all these three things, right? Cache stores for a rest less time, doesn't have retention. Database stores for a longer time, has retention. And queue usually passes it through, so stores for a very less time again. But new data storage systems like Redis, which is actually a cache or a data store, can behave as a queue, right? And queues like Kafka can behave as database. So what is happening is these systems are now diverging into something, not diverging, actually indulging into one, going into single direction, right? And so how are they able to support both the characteristics is what is how they are being designed as a data system, right? So now usually in system we keep both of them. We keep Redis as well, we keep Kafka, and connect them with application code to support our use case like below, right? So example of a data system is given. uh, a user puts an call to a data system, say, and application code is usually used to bind different systems, right? So a cache is bind by a application code to the database. So first, once a request comes, it goes to cache, it comes back to application code, and cache say maybe I don't have the data. Then it goes to the primary database returns the data which application code might put into the cache. And then what happens is, uh, maybe it was also a search query there, right? So a search query goes into a search index, full text index, and which helps us, which is again bind by application code, and returns the result, right? And similarly, at the end of the query, maybe the system put a message to message queue which is used by another application, right? So all of this different components in the data system are actually bind by application code. Now what I want to uh, show is that by using these components we are actually also building a data system, right? So okay, now coming to the meat of the part, we just understood that what we need is, from today's system we usually mean data systems, not computer intensive systems. Okay, so I will be discussing the three characteristics that are most needed in today's systems, right? So first is reliability. So going over the definition, reliability just means system should be performing as expected under the expected load. But usually many things go wrong in a system, which is called fault, right? Many things like, there could be hardware faults, say does the your disk ran out, um or there could be something like a fire in a storage, uh, there could be electricity going off. So there are many faults, right? And then there are software faults, then there may be human faults which can cause some issue in some component in the system, right? But rather than stopping these faults, which can be hard, we try to design systems such that faults do not cause failure. By failure we mean like stop the system from performing the full duty, right? So some faults cannot be tolerated though, like hacker having unauthorized access to the system. This fault can't be tolerated. There we take preventive approach then curing approach. But in other cases like hardware, software, and human faults, we take kind of a curing approach rather than stopping them. So what is hardware fault solution? Um, so what we usually do is kind of a redundancy in case of hardwares. So what we kind of do in case of disks is, say one disk is running out, what we do is we have backup disks, and usually we have rates, right? Which is array of disk which stores the data, and which is helpful to retrieve the data if anything goes wrong in one of the disks. Second is designing systems that can work with full component going down. Like say a virtual machine goes down in AWS cluster, the cluster is designed in a way that it is natural for it to go, it uh, its virtual machine to go down, and it can handle it very well. Now software faults can be something like that remain very dormant and usually affect a lot of systems. Hardware faults usually are local, uh, have local impact, but software faults have a like a global impact. And this is not we are so we are usually talking about maybe software bugs, like maybe there was a Unix bug in some years back, which had a leap year extra second, wasn't encountered for in the time system of Unix, and which led to a bug in many Linux systems, right? And it had stopped the world over systems that were running on Linux. There could be something like runaway process which took a lot of common CPU, memory, and network bandwidth, due to which other process didn't get that much bandwidth that they needed, and they ran into issues. There could be some downstream issues, downstream service or component got down and started running unusual values, due to which we failed. There could be cascading failures when small failure in one led to another failure in another component. So there's no direct solution to these things, because especially these are not very these are very rare cases that many times we humans don't think that much. And So what is can be done is maybe test more with edge cases. Artificially we can fail some components to check reliability, and allowing processes to crash and restart. So uh, so usually what is we are trying to do is maybe test the system well, and maybe what we can do is if it crashes we can restart the system, and we can monitor alerts on failures. The third type of faults is human faults, which are most common. Maybe someone so these are like someone maybe wrote wrong config or wrong code. So these are kind of uh, these can be solved on some basis. Like maybe we can have a separate region of impact from region of change. What I mean by this is, um, you write your code in you merge your code in dev, right? And you see the change in dev, right? Now once you know dev is currently working fine, you merge to stage and then you merge to prod, right? So you have separated the region of impact, which is prod, from the region of change, right? Which you have done in dev at first and then stage. Second is easily rollback. Third is like deploy to less regions first and then upgrade it. So fourth is simultaneous alerts on performance and errors. So whenever you deploy, maybe errors would help very much. Get the first get the bug that there we have deployed a bug in the prod, right? Fifth could be automation testing, and sixth could be like designing for easy interfaces. So that humans are less prone to doing errors, like design very simple interfaces and simple protocols, design simple protocols, so it is not very complex for humans to do error, like so that they can be error prone, right? uh, so that is all for reliability, but I want to emphasize that all systems today need to be reliable, such as e-commerce. Anyone except uh, so e-commerce will have a billions of dollars of losses if they are not reliable. So any system which is except anyone building prototypes need to be reliable. Moving on to scalability. Scalability is the term we use to describe systems' ability to cope with increased load, right? Scalability means system should be designed such that it can be increased with resources to handle, say, from 1 million concurrent users to 10 million. So it is not about like designing systems in a way that my current system is able to handle, say currently now 1 million, but it is also able to handle 10 million. But it is like designing systems such that it is extendable, that I can add more resources as the number of users or number of requests increases. So for learning about how we can define scalability, there are two terms we need to define. First of all, it is load, and second is performance, right? So load can be best defined as by load parameters, right? So load parameter means different from different components. Like for web server, uh, it means request per second, right? And for DB, maybe the read to write ratio makes sense for a load parameter. For cache, maybe the hit ratio makes sense, right? So in each system, we have to understand what part will cause the system load, right? So like uh, in the Twitter example, which in the book is given, when a user needs to tweet, and the tweet needs to go to all its followers, um, the system is loaded by how much the distribution of followers is per user, right? So if the distribution is very much, like if we are designing distribution, say it will be very different systems if we design for distribution uh, of followers, for follower per user equals to 1000, versus follower per user for like 10,000 or 1 lakh. It will be very very different systems, right? So you would have to think about what in your system is the blockage for scalability, what causes it the more load, that you need to define for the load parameter. Um Second term what we want to define for scalability is the performance, right? So performance is like, uh, it defines, uh, for a system that is like, performance means like how much is your system performing right now, right? So for an async system, for a like batch processing system, what it would be kind of like is throughput, how much number of requests is processed per second, right? For a web server it might be something like response time, right? For a coming incoming request, how much time I'm able to respond to that request, right? So that would matter for performance for me for a web server. So uh, but one thing I want to clarify is, in say in a web server, when we make a request, this response time differ for the same request also, right? So if you make a request now and you make the same request after 1 second, it will differ very much, right? In terms of timing. So what we do is, we kind of define it as, for a web server, what we do is we define it as in percentiles, right? We define how much. So what is a P99? We define it like, uh, how much time it would take for 99% of request to complete, right? So say I was making 100 request, and my 99 request was completed in 5 seconds, but one request was, say, outlier, and it was completing in 8 seconds. uh, so my P99 would be 5 seconds, because it is just one request that was not completing in that, right? So we define it by that. And average is not a good way to define response time. It is because, say, the average for those 100 requests that I was talking about was maybe 2.5, right? But so average was defining was, uh, my good request plus my bad request summed together divided by 100 took an average time of 2.5. But maybe my some of the requests were taking zero point 0.5 seconds, but a majority of the requests, so some of the outlier requests were taking 0.5 second, maybe 10% of the request. But a majority of requests were taking maybe like 4.5 second, right? So it is not able to predict that a majority of my request was taking 4.5 second, because it uh, includes the outliers also, right, into the weighing system. So it is not a very good parameter to define it. That's why we use P99s and percentiles. So P99s are very common. Amazon uses three nines, which is P99.9, uh, and that is what suits them, right? They saw business increase with P99.9, but when they were supporting P94.9s, they didn't seem it to very increase in sales, and it was very expensive, right? As you go on increasing your performance or reliability, it is very hard to do that, right? Increase the performance at the last scale, because one of the requests will be always be an outlier because of some uncertain conditions that we play over the network, right? Now uh, so we have defined the load, we have defined the performance, right? Now what we want to do is, with as we increase the load by the load parameter, we want to see how much our performance is impacted, right? Or with the current system, right? As we increase the load, how much is performance impacted? Or what we could do is, um, maybe we could uh, yeah, so that is what we're gonna do. And how we are gonna go, so we are gonna see that our performance is gonna decrease as we increase the load, right? So how we are gonna cope with that load, right? We don't want to decrease the performance, so how we are going to cope with that load? So there are two mechanisms usually, which is called vertical scaling and horizontal scaling. So what happens in vertical scaling is, we can increase a single server capability to handle extra load, to process more requests, right? So what we do is, say we have a server or a computer that was serving requests, right? Now what we do is, we buy a big computer, we increase the capability of the computer, the single computer that was handled the request. That is called vertical scaling. That we increase the memory of the computer, we increase the CPU, we put in more cores into the computer, so that it is able to handle more load and more requests, right? In horizontal scaling, takes a different approach, right? We add a new computing resources for servers that are stateless easily, right? So what we do is, we add more resources. So we will put two computers now to with the same uh, with same memory, not increase the memory. With same memory we can put two computers, three computers, or four computers. But one of the things that is needed is, we want those computers to be uh, stateless, right? They shouldn't have their own states, because then it becomes hard to understand once they have their own states. Now say I have four computers, uh, and they are all maintaining their states, and same one of my request goes to first computer, right? And a person's request first goes to first computer, and a person again asks his say person was asking his detail, like name, right? And maybe the name was stored by the first computer, right, not the fourth computer, not any other computer, right? Now another request comes, and by the same person, and it lands on third computer. So it doesn't have the data for that person, right? So we will be bound by each request going to the same computer. So, and that is not very scalable, right? So what we want is, usually is, when we do horizontal scale, we want the servers to be stateless, and it is a very common design pattern to the servers to be stateless. And that is why we keep the server stateless, but we make data, since database has all the data, it it is usually preferred to make the database do vertical scaling, and servers do the horizontal scaling, because those are usually kept stateless. Okay. So one thing, so that ends the thing for scalability. But one thing I want to mention is that uh, so each of the design that we do for scalability, they're specific to a particular application, right? Uh, on what load perimeters they are based, on what kind of things that they want, right? But scalable architectures are nevertheless usually built from same general purpose building blocks arranged in familiar patterns, but they have some specific design to suit the particular case. Now, the third important uh, characteristic of a data system that we want is maintainability, right? Now, maintainability usually means three things, which is first is operability. System should be easily operable and have clear metrics, helping understand how system is working in production. So what this means is system should be operable by DevOps people. It should be very easy to build and deploy those systems. So we should have a good CI/CD and deployable pipelines that automates things, right? And we should have very clear metrics on how the system is usually currently running, right? Is it healthy? Is it not healthy? Is the server functioning very properly? So they should be tools that very uh, are helpful in understanding how our current system is behaving in production, right? Second thing what we want is simplicity, right? we So developers comes and goes, but our code should be written in a way that it is easy to onboard new developers. Code should be simply implemented rather than having some small optimizations. So we shouldn't put very small optimizations uh, for a specific case. We should always try to generalize it if it is not very much needed, or if the optimization is very small. So, and if conditions should be avoided, right? If conditions can be replaced by better design patterns. If say you are writing for two objects, two different kind of objects in a same function, and you're writing if this is if I have an object of this type and another object of this type, don't use if. Maybe use a uh, different, maybe use an interface and define those two, maybe implement the interface for those two objects, right? Third is evaluability. Systems should have patterns implemented so that change is smaller in content, right? And easy to implement. Simple and easy to understand systems are usually easier to modify than complex ones. So we should have some patterns, and that's why we should also learn low level design patterns, because they are industry wide used and very common terms, and those help to contain the changes, right? Those patterns are there to contain the changes. When the requirements change, the change is contained in some place, right? So that is all for my side for data systems and the characteristics we need and how we handle those characteristics. Uh, so hope you like it. Uh, Thank you.